Okay, so you need a little help with lesson 4.1.5 homework. I don't blame you for homework questions 1 and 2 because it's a little bit funky. So it says, when methane combusts with oxygen, there is a release of energy of 213 kilocalories per mole between the system and the surroundings. And then it gives you a number you don't really need. It says the potential energy of the reactants is 100 kilocalories per mole. It says the activation energy, which is important, is 400 kilocalories per mole. The activation energy tells you how much energy is needed to break the bonds of the reactants and get the reaction going. So we have everything we need. It's just a matter of kind of reading through the lines here. So I'm going to have this go up, and since I know it's going to be an exothermic shape because it is a combustion reaction, I can even figure out what the products are because methane and oxygen is always going to produce carbon dioxide and water. So then I can label my activation energy. It says it was 100 kilocalories per mole. And it says it released 213 kilocalories per mole. So I label that as negative because if it's a release of energy, that's the correct format to show it in. That's called the heat of reaction. Now number 2 is going to ask us to draw the reverse of this. So go ahead and draw the mirror image. It's kind of easier when you draw it right next to it. And this time we're going to have carbon dioxide and water combining to form methane and oxygen. And so to figure out what the new activation energy is, we got to go back and figure out, okay, if this were in reverse from the bottom to the point where the reactants are, it's 213 plus another 100. That's 313 kilocalories per mole just to break the bonds. And then overall, the heat of reaction for the reverse reaction is always the opposite. So this would need to absorb 213 kilocalories per mole in the reverse reaction. So you can see we talked about why you don't just put carbon dioxide and water together and it makes methane gas. That'd be awesome, but it overall requires energy. And so we did cover the values of the heat of reaction for each one of these. And now let's look at which one is endothermic and exothermic. This first one is exothermic because anytime you've got the products where they're lower in energy than the reactants, that means the process released energy. And the opposite, if the products are higher in energy, then it's going to be endothermic. We've got some new pictures here for questions 5, 6, 7, and 8. It says for number 5, what's similar about these reactions? Well, they're both exothermic. They both release energy overall. But they're different because in reaction 1, it's actually a smaller activation energy. It doesn't take as much energy to break the bonds. Okay, you could also say that the second reaction has a larger heat of reaction because it's got a larger difference between the reactants and the products. And then the arrows showing the energy of activation, I drew in here how much energy it takes to get to the top of the mountain. And the one that would be more likely to occur would definitely be reaction 1, right? Because it's got a smaller arrow there, so it takes less energy to get that one going to break the bonds.